So let's begin to talk about the introduction to agnostic quantum software development with QuantumPath. In this webinar, we will talk really fast. The short reminder of QuantumPath is, and then we will talk about the different quantum approaches for problem solving we have today. To demonstrate this concept, we will create an agnostic quantum gate circuit solution, and on the other hand, we will create an agnostic annealing optimization solver. Well, remembering QuantumPath is a big ecosystem with a QuantumPath core and around that a big ecosystem of enterprise tools that led us the creation of complete quantum enterprise solutions. The QuantumPath core is the most important piece of the QuantumPath technology. The QuantumPath core provides to us the project management tools. For example, the solutions catalog. Inside the solution catalog, we then can create different quantum assets in order to solve different quantum problems with the different approaches we have today. To create our assets, we will show how to use the circuit designers to create quantum gate solutions. On the other hand, we will show how to create an annealing solution using the annealing compositor. To integrate all that pieces, we have the flow designer. We can, in a flow, define how our main program must execute all these pieces together. At the end, the goal of these tools is the creation of the agnostic intermediate language of QuantumPath. This intermediate language led us the creation of agnostic solutions that, under the hands of the enterprise BPM core, using different technologies that compile, transpile, and prepare execution units, led us the possibility to execute our intermediate language into final hardware provider and gets all the results unified to get the results and study them. So in this presentation, we will show with examples how these different pieces can work together in order to create a quantum enterprise solution. So let's begin. Before starting with the examples, I need to highlight three important information pills. The first pill is that QuantumPath provides lifecycle and solution span to products based on quantum technologies, phases, inputs, products, and cycles that allow the professional to work in an enterprise way, and not just depend on different and independent tools that must be interconnected in some way. Thanks to the lifecycle and repositories of QuantumPath, we will be assisted in the creation of quality complete solutions. The second pill is related to the two types of approaches that we have today to solve problems using the quantum technologies. In this webinar, we will focus on agnostic solutions that let us create complex solutions to solve one of these each specific technologies. On the one hand, we have the quantum gate technology. With this technology, the manufacturer has the quantum circuit as an input, a powerful tool that allows us to orchestrate the quantum gates in a series of steps, in such a way that the state of the qubit is altered until the expected result is obtained. Thanks to the known properties of superposition and entanglement, we will be able to solve in a totally new way known and unknown problems, with a level of parallelization unknown until today. Different providers will provide to you different SDKs and tools. QuantumPath, on the other hand, will provide you one agnostic way to solve this kind of problems. On the other hand, we have the technology of the quantum annealing. With this technology, the provider has as input the definition of a Hamiltonian that determines the requirements of the problem, and that is encoded in the form of a cubo matrix. With this input, the quantum machine searches for the one that requires the least energy of all of the possible solutions, being especially useful for generated optimization algorithms where there are a large number of possible variables. QuantumPath for both approaches provide us with the necessary tools to create solutions in which will not depend on third-party products and their details, simplifying variables in the solution creation equation. The third and last pillar, QuantumPath, to address the creation of algorithm and quality solutions, provides up to 3 development pipelines that will allow us to access different levels of abstraction depending on the requirements of the solutions and the developer. From the design of really agnostic solutions to solutions that depend on a specific manufacturer and its specific technology with different access levels. In this webinar, we will focus on the agnostic specific solutions. So let's begin with our quantum gate example demo. In this example, we will show you the creation of 2 circuits. The first circuit that creates an agnostic quantum incremental operation. Given a specific number of qubits, we will implement the equivalent of the operator plus plus of our really known languages. This will show you the wonderful behavior of a Toffoli gate in order to create some kind of arithmetic operations using the quantum technology. The goal of this experiment, a simple experiment to gain intuition inside a life cycle of quantum path, refactoring, compiler, and execution, different versions of this algorithm. Before start with the demo, let's get into the quantum path environment and see where we started. First of all, I will get into the system using my account. And then, from our quantum dashboard, I will go to the solutions catalog and see we have prepared 2 solutions. One for the quantum gates technologies, another one for the annealing technologies. In the first case, we have linked our solution to these quantum machines, IBM Experience, Quantum, QSharp, and QTech technologies, for example. And on the other side, for the Webinar anneal part, we will link our solution to 2 big representatives of the quantum annealing technology. In this case, the exact solver local simulator and a hybrid binary quadratic model that is installed into the cloud of the wave. Inside our quantum circuit catalog, the next step is the creation of a new circuit. We will call this circuit increment in the namespace webinar with a description of quantum increment operation. Circuit body. In this moment, we need to create our circuit. Keep in mind that we are working using the quantum gate technology. So this click on Edit Circuit button will react to this technology. When I click on the Edit Circuit button, the quantum circuit editor is open and we can begin designing our algorithm. For the creation of the incremental operator, following the classic digital design of an incremental operator, I will use the Toffoli operator. I can then drag and drop different control gates and the say not gate. This creates our first Toffoli. Then I will drag a new control to a say not, and at the end I will add a say not. Do that, you can see that we have these different gates coordinated into the circuit, and visually we can show the results before the execution in a final machine. This led us to visually react to the design of our circuit and take measures for that. In this situation, we can see that if we put as input of the circuit all the 0 stages for our qubits, we will see that the results of the algorithm will react to that, giving us the next value, 0, 0, 1. If you see that, you can see that we are obtaining the desired result. If we have an input of 0, we have an output of 1. Why? Because if you keep in your mind how the binary values are introducing into the algorithm and the binary values obtaining passing from the quantum gates, we can demonstrate that if I put the value 0 as an input, I get the value 1 as a result. What if I change the values of the input to see how the algorithm reacts? So in the quantum editor, we can these tools in our hands. For example, let me click on the stages of the circuit and click on the first qubit to put a 1. If we do that, and we show again our results, if I put the value 1, that is the 1, 0, 0, we will obtain the 0, 1, 0, that is equivalent to the value 2. Of course, 0, 1, 0. So we are visually demonstrating how our algorithm reacts. If I want to reset the value to 0, we can use the middle click at the bottom and change the stages. Well, once we have created this simple circuit, it's really important to have in our mind that when we are altering the states of our qubits, in order to measure them and get the values to be processed in other stages of our designing, we need to measure that. So let me drag and drop the measure gate. Using the tools of the circuit editor, I don't need to go again to the toolbox and drag and drop the control. Using our keyboard, for example, the Shift click button, we can copy the values of different gates into our circuit. Once we have done that, we have to keep in mind one specific question. This is not a quantum algorithm because we are not using the superposition concept. For that, this algorithm is completely statical. Even I launch this circuit 1000 times, the value I will obtain if I execute this circuit is the value 1, because the input value of the circuit is the value 0. So let me demonstrate how can we follow the process, and then we will refactor our circuit to see how the quantum path gives us all the technologies and the tools to create our life cycle to define the complete solution. So once we have defined the circuit, I will click on Save Change. I will click on Close. I will select the solution to the webinar that we will create before, and let me click on Save. In this moment, we have defined the circuit increment. In order to finalize the definition of our circuit, we need to compile it. The definition of this circuit has been done using an intermediate graphic language to define the circuit. This led us to access again to the circuit editor and recompose the diagram. Because we need to have the product of the intermediate language in order to create an agnostic solution, let me click on the button of Compile. When I click on this button, the system has launched an asynchronous operation to the backend in order to prepare the intermediate language that is in the underground of our circuit. If you need to visualize the results, we can click on the Edit Circuit, Compile Details, and we can show the result of the intermediate language that is result of our quantum circuit. Okay, done this stage, we can back to the list, and Quantum Path told us that the next step we want to do in order to create the solution is go to the flows definition. So let me click on the flows and go to the quantum circuit flows catalog in order to create our program to execute our algorithm. Well, it's the moment to create our flow to prepare the execution of our increment algorithm. To do that, let me create a new flow that we will call increment flow. In the namespace webinar, main flow of webinar incremental up. In this case, in the flow body, we need to click on the edit flow, and we visually can design the circuit flow we need to execute. To do our experiment, I will create a flow that will execute only once our circuit. So let me replace the circuit name with the name of our circuit and then connect the dots. Once that, I can click on Save Change and click on Close. I can link this flow to our webinar solution and then again click on Save. As occurs when we create circuits, we have defined the graphical version of our increment flow. In this case, we have a visual language in order to recover and edit the flow wherever we need. Okay. So in order to have the product, we need to publish our executions. We need to compile our increment flow into our intermediate language. To do that, we can use the different editor buttons of the flow or the direct access of the compile action inside the list. So let me click on the compile. Once we have done that, again, the backend process the compile option. And if we go to the edit button of their details button, we can see the compile details. We have the flow in our abstract language. Once that, I can go to the backlist, and in this specific situation of the flow, we have compiled the intermediate language. The next step is to transpile the flow. When we click this button, the system in the backend will create all the stuff on the semi-intermediate language that is specific of each fabricant homologated into the platform. So when we click this button, we have all prepared and published in order to create an execution. Once that, I can click on the runtime dashboard. In this situation, we have access to the Quantum device, to the Quantum runtime dashboard of QuantumPath. In this Quantum dashboard, we can see the different Quantum devices mapped to our solution, as we saw at the beginning of the demo. We have in the right panel the commands pane that show us how many runs are doing in the platform for our solution, and the results pane in which we can show the results and the exceptions if one occurs. So in order to make this experiment fast, let me click on different simulators. The IBM QSM simulator in the cloud, the QSM simulator deployed into the backend of QuantumPath. Let me click on the QDK simulator we have in the backend of QuantumPath and the QX single node simulator of the QTech cloud technology. Selecting these four machines, we can click on the run flow, and QuantumPath will start the experiments in these different quantum machines. Let them run one moment in order to finish the executions. As they are finished, we can click on result and we can get the results as they are finished in the runtime. Okay, as we can see, if we click on this QX node simulator that just finished the first, we can see that the webinar has, for the input of the value we put at the beginning that was 0, the results are the value 1. So it's just that we expect. Of course, at the end of all of these results, we can show that all the machines are returning the same values. For the 0 input, the results are the value 1 with a probability of 100%. So once we have that, we have the experiment working. But what is the problem? That we are using a static input value and we are obtaining one static output value. So we have gained the experiment demonstrating that the increment works, but we need to do this experiment quantum. So how can we do that? Okay, let me go at the beginning of the circuit and let me refactorize it. For that, we will go back again to our circuit catalog. We will select the Edit Increment circuit and then click on the Edit Circuit button. In this case, we recover our design. How to make this algorithm quantum? Okay, let me put the Hadamard gate at the beginning of our circuit. I can drag with the shift button, and I have our circuit quantumized. What that means? Putting the Hadamard gate at the beginning of the circuit, we are creating the superposition state for the next of the circuit. In this case, at the end of the solution, we have the 50% probability values to have the 0 or 1 value after proceeding our algorithm of incremental. What that means? When I make an iteration of this circuit, the input could be 0, 0, 0, 0, 0, 1, 0, 1, 0, aleatory. We have infinite probabilities to have all of these values as input. Whatever value we input to the circuit, at the end, the result value will be the input value plus 1. So in this situation, our visualizer are explaining to us that for whatever probability we have of the input values, we have a specific probability of result value incremented in 1. Okay, so how can we demonstrate that? Okay, so let me click on the Save Changes, close, and save our circuit. Due to we have changed our circuit, let me click on the Compile button to update our intermediate language. Once that, we can go to the flow, and we click on the Edit Flow. In order to demonstrate that we can create different summatory options for different probabilities of the input values, we need to repeat our experiment some kind of number of times. If we don't do that, if we run our experiment, we need to run different times to obtain different values. To avoid this situation of execute one by one the operations, we have in the flow editor the possibility to create an iteration. To do that, let me click on the flows and let me drag and drop our iterator icons. For example, from 0 to 500 times. Then let me connect the dots so we can drag and drop to the increment, to the flow, to the end. Once that, the result of this flow will execute our increment execution 500 times. Let me click on Save and Close, save again our circuit, and as occurs before with the circuit, we need to recompile our increment flow. For that, let me click on the Compile button. On the back end, the flow has been compiled in intermediate language. Because we have to do that, we need to transpile all the products to update our solution. And once do that, we need to click on the execution of the runtime dashboard. Again, in this pane, we need to choose different machines to prove our algorithm. So let me click, for example, on the QDK and the QSAIM and the remote simulator of the IBM on the cloud. Then let me click on the run flow. Again, we are launching our experiments. Let me show you the time we have the experiment launched. So as this experiment is being finished, we will refresh the pane in order to get the results and show how results our quantum machines are giving to us. So wait a minute, one of the experiments has been done. So I can click on the refresh button, and here it is. The different results the machine has returned to us are the different numbers that are the results of the increment, the qubit aleatory sets, thanks to the Hadamard operations. So if I click on refresh, we have all the results of the different machines in which we have launched the experiment. So with this example, we have seen how easy is the creation of a solution, the creating of a circuit, the create of the flow to execute our circuit, and the execution, the results examination, and the refactorize of the circuit in order to create a quantum incremental operation. To finish this first quantum circuit demo, we are going to show the Grover algorithm. I recommend read the algorithm theories to learn more about what it does on the pages of the Qiskit SDK or Quantum Inspire or Microsoft QPath. In these pages, you can see easily how the algorithm is solved using different approximations from the different hardware providers. Especially, we recommend the lecture of the Quantum Inspire website in which this demo is based. Well, let me tell you that as a quick summary of this algorithm, we will say that it's a totally new way of looking for an element in an unstructured database using a complexity that breaks with the classic. To do this, we will use a resolution of 3 qubits and a definition of an oracle that will identify the value 6110 over all possible ones, and 1 or 2 steps of the diffuser to improve the probability of occurrence. Using the quantum path editor, we can visually see how we progress and how the encoding of the circuit accelerates before iterative stages of the circuit. So let's begin to codify this circuit. And then let's go back to the quantum path environment, and we want to create a new quantum circuit definition. I previously put in the metadata needed, following using the quantum gate quantum type technology, and I will click on the edit circuit button. In this case, I will edit our circuit following the instructions of the quantum inspiring experiment that tests the groove algorithm. In this case, first of all, we will codify the oracle and then the diffuser, following the instructions. So in this case, we can see that in the real life, some of the engineers of our team can design the circuits, and then when we have the design of the circuit in paper or whatever, we can put inside the circuit editor. Let me a minute. First of all, I will design the oracle following the instructions. So I drag the CNOT gate, then the Hadamard, then I will drag a TOEFL using the control click. I can do it really fast. And then again, I will put a CNOT and a Hadamard. Okay, this is the oracle. In this case, we can see that for an input of 000, the result is an amplitude of 000, but you can see that the phase is put on the 0 state. Well, if I click on the state and put the 011 that codifies the value 6, we can see in our quantum amplitude visor that the phase has put on a value different from 0. So we can say we have the value 1. So we can demonstrate with that the oracle works. Let me reset the values to 0 again. And now the next step is to codify the diffuser. The diffuser has the responsibility to magnify the probability of the value that the oracle sets. So for an aleatory input of 3 qubits, the diffuser will amplify the oracle result in order to search the value we are searching for. Let me a minute to codify the diffuser. So for that, I will drag the edge or copy the edge again. The next row is codified using CNOT, so I can click and copy. Then comes a TOEFL. In this case, I have the TOEFL previously designed, so I need to copy the row. And, oh, excuse me, I forget some edge here in the circuit, so I can introduce it with drag and drop. And we have the first part of the diffuser. Now I have to invert this part. So for me, it's so easy because I can click and invert the position of the gates. So I have a version invert from the source of the diffuser. I forget following the instructions a column of CNOT. No, that's okay. So we have here implemented the diffuser. In the theory of the algorithm of groove, we can put 1 or 2 steps of the diffuser in order to magnify the probability more or less. In this case, we will use the 1-stage diffuser for our experiment. Well, before that, we can click again on the value 011, and we could see that the results of the different amplitudes at the end, we are searching for the correct value. So in this case, the amplitude of the oracle demonstrates that we can find the value 6. Okay, in order to make this algorithm quantum, I need to put 3 Hadamard gates at the beginning of the circuit. So in this moment, we have 50% of every probability value of the input. So we could see that the system is working again. The amplitude is 100% in order to find the value 166. And at the end, I will put the measure in order to get the results of the histogram and take them to analyze at the end of this exercise. Well, once we have all the circuit designed, I can click on Save Change and close the dialog. We have here the visual representation. I can click on Save, and as we done before in the previous examples, I only need to click on the Compile option. In this moment, we have the groove algorithm codified in our intermediate language, okay? So let me go to the flows, and we will create, let me a second, please. I will copy the name of groove, okay? Then go to the flows, and I will create a new flow that we will call groove flow with the webinar namespace, description, flow to groove. In the flow body, as we did before, we click on start. I put an iterator, put the groove name. We will repeat in this case 1000 times, and I will connect the dots. Okay, so in a minute, I connect the dots. Okay, let me save changes. We have our main algorithm codified. I click on close, select the webinar solution, and click on save. Well, once I have done that, again, I need to compile our flow. Once the flow has been compiled and we have the meta language generated, I can click on the transpile button. So now the backend of QuantumPath is preparing all the physical assets that are needed in order to execute our algorithm, and then goes to the runtime dashboard. In this case, again, we have different machines, and we can choose, for example, the QX simulator and the QSAIM backend QuantumPath simulator. In this case, this is in the cloud, and in this case, is in our backend. I click on the run flow. The jobs are in execution now. We can wait a few seconds in order to finish the executions. As soon as the job finishes, I can refresh the results and study them. One job has finished. I can click on the results. This is a job pending now. So while this job finished, we can solve the results, and we can see that the value 011 has been executed, and the 33% has been detected, and the 110.78.2, that is the most high probability of the value we are found. The rest of values probably will be obtained due to errors or random conditions. I can click on the refresh button because the second job has finished, okay? So 0.4 minutes, 0.2 minutes, the QSAIM local simulator has been fast in this case, but in the two situations, the value 110.782, and if we search in the QX experiment, we have the value 6 with the 0.79. So in the two cases, the value 110 has the most probable value that we can find in our histogram. So we have demonstrated in this experiment that the groove algorithm works as we expect. Of course, we can refactor the algorithm, adding a new step, so we can see that in this case, if we re-execute our experiment, probably we augment the probability of the appearance of the value 6 at 90%, more or less. So let's go to the following example, for which we will use the quantum annealing technology. For this example, we will solve a typical optimization problem. We want to optimize a package delivery. For that, we have 5 boxes, each one with a specific weight and a specific price. We need to obtain the best combination of weight price to fit a maximum weight about 6 kilograms.
To better understand how we have solved the example, I will briefly explain an analysis of the problem. To optimize the package delivery, we need to define one class that we will call box. For this box, we need to define 5 instances. Each instance will have its own characteristics, for example the price and for example the weight. For each instance, every price and every weight we will have as input the values we have defined before. To solve the problem, we need to have 2 rules. The first rule is determine the weight of the packages, that must be 6 kilograms. And the second rule, that we want to maximize the price. In order to solve that, we need to define these mathematical expressions. The first quadratic can be developed as we can see in this part of the expression. The second rule must be developed using this linear term. In order to do that, we will see how the quantum annealer editor can help us to do that. We have to keep in our mind that we need to do a little magic adjusting the lambdas, but of course this is out of this webinar and will be taught in another moment. At the end, the background of this problem consists in the definition of the Hamiltonian that solves the combinatorial problem and the QPath generation. So let's QPath help us.
With our solution ready, the next step is to create the circuit. In this case, we will create a new circuit that we will call boxes. Our namespace webinar, boxes optimization, and then here comes the most tricky part. First of all, we must select we want to use the annealing technology. So the edit circuit will open us the quantum annealer compositor, a great tool to simplify the process of the definition of the annealing problem. Well, we will follow to the classes. As we told in the presentation, we need to define a variable, a new class, that we will call boxes. These boxes, we need to define 5 instances, and the prefix we will put to the boxes will be box. Okay, then in our box class, we need to define specific properties. One property to define the price, and other property to define the weight. So, to do that, we will go to the Properties button, click Add, and we can find that the editor generates for us the 5 instances. So, here we will put the values we have registered in our demo. So, 4, 1, 3, and 5. And we will click on Save. Of course, this property must be called price. And I will click on Save. We need other property. This property we will call weight. Is the other property we need to store from our boxes. And again, we have our 5 instances, and we can specify the value for the weight base. So in this case, we will put the values we have defined in the presentation. 1, 2, 3, 4, and 4. And click on Save. Now we have defined our class definition and our 5 variables instances of boxes. So let me go to the next step, that is the definition of the rules. Once we have defined our class, the next part is to create the rules. Remember, as we told in the presentation, that we have to generate a formula that codifies what is our problem. For that, remember first that we need to create a rule that establishes that we have 6 kilograms as maximum weight and we must combine our boxes in order to sum a top of 6 kilograms. Applying these two terms, one for the linear in order to establish the maximum weight and the quadratic term in order to create the combination, if we solve this formula, see this mathematical formula, we will obtain this expression. First of all, we have this expression that establishes the weight, and the second formula, how our elements must be combined in order to establish the maximum weight. To do that, we will do the next rule. First of all, we need to add the rule, name rule 1, and description. We will put that the weight must be 6 kilograms. In order to codify these two expressions that we must put in our system, let me create two interactions. The first interaction is a linear interaction. You can see that QuantumPath provides a simplified version of the formula in order to assist us in order to the creation of the terms. So the first term we must define is the summation term. In this case, I can add some iterations as needed in order of the number of dimensions of the problem. In this case, we have only one dimension, so we only need one summation. In this case, I will add the summation part. I will put any number of the name of the variable from 0 to the term boxes. In this case, I will put the name of the class, and the system will automatically determine how many elements must be iterated in order to solve this part. When I define this part, I click to the OK. OK, we have a visual representation, and we have an error because we haven't finished yet the definition of the formula. The next part is the coefficient. In this case, we need to put an expression that let us to calculate how the items are related. In this case, as we define in our formula, we must put the elements we have minus 2 times the weight. So in this case, I will copy this formula. I will paste in my pane and click OK. As you can see, we are developing this part of our Hamiltonian. Okay, the next term is the iterator. So in this case, we have the variable e defined, so we put the variable a. In this case, we have finished the define of the first linear interaction. Again, we need to define a new interaction more. So to complete our first rule, we need to create a new interaction. In order to do that, we have to create this second part of our formula. We have made a mistake because this must be 2 sigma in order to iterate all the elements. So let me correct that in the real case. So I need to click on the add again. We need to choose that we need a quadratic term, and we start with the summations. Of course, we have 2 sigmas. So the first sigma, we will put the variable a, y, and goes to 0 while the number of boxes. And iteration of 1. We need to add a new summatory, a new sigma. So in this case, we will put the variable j. In this case, we will go through the I plus 1 elements to the number of boxes. So you can see how easy is the creation of the cubo matrix, creating our sigma following the equation that our mathematical team has developed for us. Well, when we have these 2 sigmas, I can click OK. We are seeing how the formula is being finished. So let me go to the coefficient. In this case, again, we will have to put how the elements interact between them. So I can click this expression and click on OK. Again, we must define the terms of the elements. So the first term is the y, and the second term is the j. And I click in OK. So we have finished our formula. You can see, following that we are very similar with the terms we need to define first. Well, once do that, we can click on Save. Again, we can click on Save, and we have defined our first rule. To finish the example, we need to codify a new rule. This second rule is the rule that we want to use to maximize the price. For that, we have to create a rule that uses a linear function of maximization. In this rule, interview all the variables with all their prices. To do that, we have pre-created the rule into our quantum path environment. So if I click in this rule of price maximization, and the same we have done before, we have created the rule, we have put the description, we have to select lambda about 1.5. We will talk later why that. And then for this interaction, we have created a linear type. If I click on the details, we can see we have the same pieces of a formula that before. So in this case, we have added one summation using the boxes at the same that before. We have specified the coefficient that uses our boxes item property price. And then we have specified a term I that is the iterator of the formula. Once that, we have our formula ready, so we have to click on save, and we have all the rules codified. So that's the definition of our problem. So let's get the rest of the pieces of the puzzle. Well, we are ending our demo. To finish demo, we only need to remind you what was the combination of boxes we have at the beginning. Of course, we can see that the combination of box 1, 2, and 3 is the best option that maximizes the weight and the price. So let's demonstrate that. Well, we are running out of time. We have just prepared our solution box flows. In this case, this solution has a flow predefined that combines the execution of the boxes annealing process. Okay, once that, remember that we have to compile our solution in order to get the intermediate language of our flow, then push the transpile button in order to create all the assets that are needed to prepare the execution process, and then we will click to the runtime dashboard. In this case, we have previously proved our algorithm and validated it. Of course, we will repeat the operation. In this case, we will click on the D-Wave exact solver. This is a local solver installed in the backend of QuantumPath, and then we will execute the experiment in a real machine of the D-Wave into the cloud. Okay, if I click on run flow, all the processes are running now, and we will see that the results that large. Well, if I refresh, we can see that we have first the result of the D-Wave exact solver local simulator, and we could see in the results that we have in the full sample result that the box 1, 2, and 3, based on the 0 index, have the 1 value, and the rest of the boxes are codified with 0. That means that the exact solver has been found these boxes. In other webinars, we will talk about why in this first experiment we have the box 4 with the 1 value. This is result of a bad lambda selection. Okay, let's wait a minute until finish the cloud machine of the D-Wave. We must expect that the result must be the same. In order to wait some seconds, we could see in our historified executions that we have executed previously this experiment. In this case, this machine returns the same result as the local machine. So in this case, this result was obtained from a physical D-Wave machine. Okay, let's wait a couple of seconds to finish the experiment of the D-Wave E-read binary quadratic model solver and validate that the experiment has been a complete exit. Well, our experiment in the remote solver machine has been ended. If I click on the refresh button, we could see that the D-Wave solver has been finished the operation after 2 minutes, and we can validate that the results are correct. The box 1, the box 2, and the box 3 has been returned with the 1 value, so it's the best combination. So that's all. Thank you all for attending our webinar. We wish and hope that all of you and yours be okay. Please stay safe. See you in our next webinar, Developing Classical and Quantum Hybrid Software with QuantumPath. See ya!